Right, have you written that equation? Nine, 8, 7, 6, 5, 4. Waste less time saying no, more time writing. 3, 2, 1. Right. This is a very exciting day for you. It's your first redox reaction that you're going to balance. Okay. It is. Good question. It is a long but easy process. Okay? We are going to start off, and all these steps are on the website. We are going to start off with our equation, and I've told you it's a redox reaction. And I'm going to ask you to balance it using a special method called the ion-electron method. So we're not balancing like we used to do. We're going to use this nice, long, boring, but quite easy method to balance it. First of all, with my black pen, if you have different colours, you might want to do it with different colours. I'm going to underline any ionic compounds that I can see in that equation. So perhaps, Luis, could you point out one ionic compound in there?
Potassium permanganate.
Potassium permanganate.
Yeah.
Ionic, good. Someone else, I know another ionic compound you can see there, possibly. Potassium chloride, actually it's already underlined in red for some reason. Let's make it black. That is ionic. Anyone else? Alberto, are there any other ionic compounds in there?
Yes. Yes, please. Manganese chloride, please.
Thank you. Right, they are ionic. Next thing, in a red pen, I'm going to underline any acids. Diego. Hydrochloric acid is one. That is an acid. Any other acids? No. Which means the other things there could be possibly metallic, but are likely to be covalent. Which are the covalent things then in S? Yes, covalent. Water, covalent. So the first, perhaps the most boring, time-consuming step, we are now going to write the exact same equation again, but we're going to separate, as we've been practicing, any acids and any ionic compounds. So we're going to end up, and I suggest you start right at the left of your page, keep it reasonably small so it fits. So, I take my hydrochloric acid, which is going to break up to form an H+, like all of our acids always do, and a Cl-. That is separated. Next thing, potassium permanganate. I'm going to get my potassium plus, and I'm going to get my permanganate, which has a negative charge. You can see already I'm taking up lots and lots of space, and I've still got lots of things to write. Do covalent compounds break up when dissolved in water? They don't, so I can just leave Cl2 as it is. Potassium chloride, we said that's ionic, it's going to give me my potassium plus and my Cl minus. Alberto, or possibly Leopoldo, identified the manganese 2 chloride.
Yes.
So I'm going to have manganese, 2 positive charges, and I'm going to have 2 chlorides, 2 Cl minuses. Finally, water, covalence, that hasn't split up, I can write that just as it is. There we go. Long, time consuming, a bit boring. Luckily, it is going to keep being very exciting. What are we going to do now? What did we do with our practice ones next? What might I want to identify about everything there? The oxidation states of each thing. So, David, You're going to take us through this. 8 plus.
Plus 1.
Plus 1. I'm going to write numbers. You can use Roman numerals if you want. Up to you. David, next one. Minus 1. Good. Next one. Plus 1. Good. Next one. What's oxygen always? Minus 2. What must manganese be there then? Don't just say what other people said. Use your brain.
Plus 7. Plus 7. 8.
Oh, we've had 1.
Plus
2,
7.
7.
Plus 7.
In this case, you can use our little maths trick to work that out. It must be plus 7, because when I add plus 7 to the 4 minus 2s from oxygen, it equals minus 1. Diego, take over. I've got chlorine in its elemental state. It's on its own. There's no charges. What is it going to be? Very good, Luis. Careful. Next one, Diego. Potassium with 1 positive charge only.
Plus 1.
Plus 1, fantastic. Minus 1, good, keep going. Plus 2, fantastic. You've got ignore 2. Good. What's oxygen always? What's hydrogen? Fantastic, good. Diego, oxidation number specialist today. Yeah. Okay. Can we make this process more exciting? No. Why would we make it more exciting? When we are talking about redox reactions, what are we interested in? What does redox mean? Reduction and oxidation. What are we talking about moving when we've got reduction and oxidation? Electrons. So we need to find now the two things, the two reactants, or the two bits we've got that have changed their oxidation number from the beginning of the reaction to the end of the reaction. So can someone identify one element there that has changed from here to there? I'm going to ignore you, Ina. I'm going to go on, tell me one, Fran.
Manganese.
Manganese. So I've got this thing here, where manganese is plus 7.
Yeah.
Afterwards, manganese has become plus 2. Now, my oxidation number for manganese has gone from plus 7. It's gone down. It's become more negative. If something becomes more negative, has it lost or gained electrons? It's gained electrons. Can you remember our mantra? Oxidation is loss. Reduction is gain. I'll tell you about that in a moment, Manu, because you weren't here. So, that process there is reduction, because the manganese must have gained electrons for its oxidation number to drop, to become more negative. Who have I not heard from? Paula. Which other element here has done the opposite? It's changed its oxidation number and become more positive.
Hydrogen?
It is going to be, well, hydrogen there is plus 1. Over here it's still plus 1. No.
Chlorine?
Chlorine, what have we gone from? Minus 1 to 0. Fantastic. Over here we've got another minus 1, and that's minus 1. We can ignore them. But here, let's use a different colour. Chlorine has gone from Cl minus, minus 1 oxidation number, to a chlorine molecule. So that number has gone from minus 1 to 0. It's become more positive, which means it must have lost electrons, which means that we have oxidation. Right, if that has not excited you enough, we're going to make it even more exciting. We are now going to write a separate equation, a small equation, a mini equation, which we call a half equation, for each of those two processes we've just seen there. So, for example, for my oxidation process, we've identified that we've gone from Cl minus to form Cl2. You'll notice I'm leaving lots of space around in case I need to add numbers and things, which I will do in a minute. For my reduction, we've got my permanganate, and I'm using that whole thing where my manganese is. That is becoming a manganese 2 plus ion. Again, leave lots of space because we're going to add some things in a moment.
Mr. Canning, how many times do you expect us to do a redox reaction?
How many times will I?
You expect us to do a redox reaction?
For the exam.
For example, how many?
It will take time.
So
That will be taken into account, don't worry. We may even do one like this as a kind of separate test, because it does take time. Right, we now, with our half equations, we need to balance those half equations. So, to balance our half equations, this just becomes just really nice and exciting. If I look at my first half equation, which is to do with only the oxidation process, I've got 1 chlorine on the left, 2 chlorines on the right. So how would I balance that if we were doing it the normal way we do it? Mark, I'm going to put a big 2 there. Okay, I now have 2 chlorines on both sides. What is not balanced in that little half equation? Mark, twice in a row. The charge. At the moment, I've got 2 electrons, or 2 negative charges on the left, but everything on the right, I've got nothing with any charges. So I've got 2 on the left, nothing on the right. Now, because we are talking about an oxidation reaction, I am allowed, and this is one of our rules, I'm allowed to now balance this half equation using electrons. What charge is on an electron? Yeah, a negative charge. So where could I add electrons in this half equation so that overall I have the same charge on both sides? David, go, inspire me. Be confident, ignore Leopoldo.
one electron from chlorine.
I'm just going to add them. I'm going to imagine I have a jar of electrons and I'm going to add whatever I need. How many do I add over here? This is how we're going to represent an electron with an E minus, because it's an electron, it's got a negative charge. Fantastic. I need 2 electrons on the right side because now I've got 2 negative charges on both sides. Okay, which means they're balanced. We don't have to have neutral on both sides, they just need to be the same using our electrons.
We can only add electrons, but we cannot add protons.
No, exactly. Only electrons because this process we know electrons are moving around. Right, that is now balanced. What about the reduction one? It's a bit more complicated. It's a bit more complicated. Let's first of all, let's look at our interesting element and let's try and balance that. Let's look at my manganese. Paula, how many manganeses are there on both sides? 1 and 1 on the other side. Fine. Don't need to do anything about it. What is not balanced though, Paula? Oxygen. Now, these redox reactions, we are always doing them in solution. You can see we've got some water there. We're doing them in solution. So, to balance my oxygens, I'm going to use water. Where can I add water? And Paolo, I'm going to stick with you. Where can I add water? And how many to balance the oxygens?
On
This side, yeah? How many? How many oxygens on the left? 4. So how many waters do I need on the right? I need 4. Perfect, my oxygens are now balanced. However, David has identified a problem. Now I've got hydrogens. Luckily, what we learned at the beginning of this week, what do acids always release when they dissolve in water? H plus is hydrogens. So my next step, once I've added water, is to balance the number of hydrogens using H pluses. So, who's going to answer? Antonio, how many hydrogens do I need to add on this side? I need 8. And remember, they are positive hydrogen ions. I need 8 H pluses on the left.
And we got in the reaction with water and hydrogen always.
You will almost always have to add them. Now, finally, very quickly, like with my first half equation, I now need to check the charges are balanced. On the left, I've got a negative charge on my permanganate. I've then got 8 positive charges from the hydrogens. So overall, I've got 7 positive charges. On the right, I've got 2 positive charges overall. So I'm going to have to add 5 negative electrons to the left, so that overall the charges are balanced.